It is with immense pleasure and excitement that I have the chance to introduce today Dr. Daniel Wolpert. I must emphasize that actually he was our first choice, and not only he responded positively, but he did so in a lightning fast fashion. So I want to thank him for that to begin with. For those of you who don't know him, I don't think he requires much introduction, but I'll just do quick something. He has his medical doctorate degree from Cambridge, also continued his master's degree in the medical science area, got his a doctor of philosophy in physiology in Oxford, and after a number of other events now, Dr. Wolpert is the director of the Sensorimotor Learning Laboratory, using different approaches to probe underlying principles for skill acquisition and skill control. One of the perhaps unconscious but very important criteria for me to select him was to make sure that he had an OptiTrack, and he does have two. So I just want to thank again, I guess, NDI for their support, and I also want to acknowledge the support of Human Kinetics. I don't think that somebody that doesn't be introduced would be taking any of his time, more of his time off. So without further ado, Dr. Wolpert.
Okay, well, I'd really like to thank the organizers for inviting me to this meeting. It's actually terrific and a pleasure to be here. Today I want to tell you about some of the work we've done in trying to reverse engineer how the brain controls movement. And in my lab, we focus on the upper arm and hand, not because it's the most interesting part of the body, but because it has all the features that makes control hard. So we've got multiple degrees of freedom, which makes control hard. It's highly nonlinear. It's time varying. The properties change over time, both on a short time scale and a long time scale. It's got long time delays. And we've worked on all those attributes over the years, but the one I'm going to focus on today is the issue of noise. It's an area which we've got particularly interested in the last few years, and it's an area which actually brings us a unifying framework to think about motor control. And I think you're probably all familiar with this, that when you send a motor command down and you get sensory feedback back, these signals are not beautiful signals as you would wish them to be. Sensory feedback itself is extremely noisy. You put your hand under a table, try to localize it with the other hand, you can be off on the order of 5 to 10 centimeters. Similarly, the motor command itself is extremely noisy, as you all know. Try to play darts making the same movement each time, you get a very different movement. And more than that, the outside world is both ambiguous and variable. For example, this teapot could be full or empty, and it can change over time. And so we work really in a whole sensory, motor, and task soup of noise. Now, this noise is so great that society places a premium on those of us who can reduce our overall sensory motor noise. As you and Stuart Biddle will be very clear, if you can, for example, knock a small white ball into a hole several hundred yards away using a long metal stick, and you can do that accurately and repetitively, well, you can earn hundreds of millions of dollars of our society. It's a very bizarre thing that our society appreciates those of us who can reduce this noise. But I want to convince you, it's not just society who cares about this noise. The brain goes to a lot of effort to reduce the negative consequences of the sensory motor and task noise. And to do that, I'm going to tell you about 5 things if I have time. I'm going to tell you about some work we've done on Bayesian learning, asking whether the brain is a Bayesian learner. I'm going to ask about how the brain predicts consequences of the action, how we evaluate the outcomes of actions, how we make optimal decisions, and finally, how statistics of task affect the way the brain learns things. Now, I'm told that not all of you will be totally familiar with Bayesian statistics, and so I'm going to give a 5-minute introduction for those who don't know anything about Bayesian decision theory. If you don't follow this introduction, don't worry, it doesn't matter for the rest. If you know about Bayes' rule, you can sleep for the next 5 minutes. But the reason I'm going to tell you this is we think it's a very important unifying framework of how the brain should deal with variability and uncertainty. So here's Thomas Bayes. He lived in the 1700s. He was an English cleric, a vicar, and effectively he wasn't particularly famous in his life. The only thing he was famous for writing during his life was a defense of Newton's ideas, which were under attack after Newton's death. But after Bayes died, a friend of his found an interesting mathematical proof among his papers and thought it so interesting, he sent it into the editor of the Philosophical Transactions of the Royal Society, saying, I now send you an essay which I found among the papers of our deceased friend, Mr. Bayes, and which, in my opinion, has great merit. Now, fortunately for us, the editor at that time is not as difficult as he is today and didn't ask for major revisions, given that the author had been dead, but instead published it as it was, essays towards solving a problem, the doctrine of chance. And it was really forgotten about for hundreds of years. But from the 1950s onwards, it's become a major plank of statistics and machine learning, and more recently a unifying way to think of how the brain should deal with uncertainty. And effectively, there are two components to Bayesian decision theory. There's Bayesian statistics, which is about making inferences in the world based on uncertain information. So identifying the visual identity of an object, whether it be an apple or a pear, knowing where your arms are in space, for example. And having made inferences about the world, the second component is decision theory, which says, given those inferences, what's the optimal action I should take based on those inferences? So here's the introduction. The idea is there are two sources of information. There's data, which comes into the system. In our case, that could be sensory input, or it could even be motor output as well. And then there's prior knowledge. For example, memory, knowledge about the world. And we want to combine those two sources together to generate beliefs about the world. And it can be beliefs as simple as where are my arms, as to what are you thinking. So these are beliefs we want to generate and estimate based on uncertain information. And what Bayesian statistics says is the best way to represent beliefs is through probabilities. So we're going to represent degrees of belief in different propositions as probabilities. So the strength of belief will have a given value between 0 and 1. 0 means I'm absolutely sure it's not true. 1 means I totally believe it's true. But I can have gray scales in between 0 and 1 for my probabilities. So we can write P of A is the belief in proposition A. So I could say to you, if I should throw a fair dice, what's the probability it'll show a 6? And you could say, well, my probability, my belief in that is 1 out of 6. Or I could ask you, what's your belief that all ravens are black? And you might say, well, I think 0.95. I'm 95% sure that all ravens are black. But there's a good chance there could be a white raven out there. And in Bayesian statistics, we're even willing to deal with problems which can never be answered. We could ask, what's your belief that Fermat would have understood Fermat's last theorem, the proof? And that's something we can quantify as well. So we have beliefs about the world which we quantify as probabilities. And there's one more element we need to get to Bayes' rule, and that's the idea of a conditional probability, which is the probability of one thing given another thing is true. So the vertical line here just means shorthand for the given. So P of A, vertical line B, just means probability of A given B. So if I say to you, what's the probability a dice will show a 6 given it was even? Well, you know there are three possibilities that could be even, and therefore, there are three possibilities for it being even. One of those is a 6, therefore the probability of a dice showing a 6 given it was even is 1 out of 3. We now have all the machinery we need to develop Bayes' rule. Imagine we look at the people in this room and we decide whether they have event A being true about them and another event B being true. Let A be some particular disease and B be a positive blood test. We could choose someone at random and say, what's the probability that both those events are true? That's A and B, and I write that shorthand with a comma. Well, let's make it a bit simpler. Imagine there are 10 people in the room. Here they are. Some, those in white, have neither the disease nor the positive blood test. Those in blue have the disease. Those in red have the positive blood test, and some have both. Well, we can answer this question very simply. We can now count it up. The probability of having both is very simple. It's these 3 people here, and there are 10 in total. So the probability, choosing someone at random, which has both those events, is 3 out of 10. But we can write that in a different way. We can write it instead as the probability of one of the events of being true of the person we choose, multiplied by the probability of the second event being true, given the first was. So let's have a look at this and check it makes sense. What's the probability of B, the positive blood test, if we choose someone at random? Well, that's very simple. There are 5 people here, the ones in red, who have the positive blood test. Therefore, we've got a 5 out of 10 chance of choosing someone with a positive blood test. And what's the probability of the disease given a positive blood test? Well, of those with a positive blood test, 3 of them have the disease, 3 out of 5. And so reassuringly, 3 out of 5 times 5 out of 10 gives us back our 3 out of 10. Or we can write it the other way around. We can write it as the probability of having the disease, multiply the probability of the positive blood test given the disease. So let's have a look. Probability of the disease, well, that's very simple. That's 4 out of 10. And of those, what's the probability of having a positive blood test? Well, that's 3 out of 4 in this case. And so 3 out of 4 times 4 out of 10 is again 3 out of 10. So mathematically, all these 3 things are simply mathematically equivalent. So we can get rid now of the left-hand side, and we just have an equality relationship in probabilities. I mean, now we can divide both sides by the same thing, probability of B, and rearrange it, and we get Bayes' rule. So Behaviour is nothing but a consistency relationship among probabilities. It's a mathematical truism. It just says I can work out the probability of A given B as a function of these three things here. Why is that useful in statistics? Well, imagine you're a doctor. Someone comes in, they've got a positive blood test. It would be very nice to know the probability of having the disease given a positive blood test. That's part of diagnosis. Well, it turns out that's hard to work out in one go, but by plugging in these various things here, which are things like prevalence of disease, prevalence of positive blood tests, and so on, we can estimate these parameters to work out the diagnostic equivalent. Right, that's fine for statistics. What's it got to do with the brain? Well, let's relabel A and B as things we care about to do with brains. Imagine that A is the state of the world, something you want to estimate about the world, where your limbs are, whether you're looking at a polar bear or a fox. And B is sensory input. Wouldn't it be nice to be able to say, what's the probability of different states of the world given sensory input? That's part of perception. If I could get some visual input and say, how probable is it I'm looking at a polar bear compared to a fox compared to a cat? That would be a very useful thing to do. Well, it's hard to do that in one go, but by plugging the A's and B's into Bayes' rule, we get something which has much more intuitive appeal and maybe simpler to estimate. So here I've just plugged in those parameters, sensory input and state of the world, into Bayes' rule. So what do we have? Well, over here, we have probability of different states of the world independent of sensory input. Okay? So this is the prior beliefs about different possible states of the world that can exist. So, for example, how probable is it I'll see a fox today compared to a cat? How probable is it my arms will be in this configuration in general compared to this configuration? These are all things I can learn through the course of my life and estimate as the probability of different states of the world independent of what's happening now. So we call that the prior. That's the prior belief about the world. But then you get sensory input. And clearly you're going to have to update your prior belief in some sensible way. And what Bayes' rule says is the thing you should do is say how probable is the particular sensory input I'm getting now given a particular state of the world. And unfortunately it's got a horrible term, the likelihood, these horrible mathematical terms. But basically it says, how probable is it that I get this visual input if I'm looking at a fox, and how probable is it I'll get this visual input if I'm looking at a cat? And if I can quantify my prior and my likelihood, then I should multiply them together. This is a normalization term I won't discuss, and what I get is my belief in the state after sensory input. And the point is that I can estimate these things, my prior and my likelihood. This is the optimal way to update my belief about the world. And to do that, I generate what's called the posterior. And then I can effectively iterate this process based on my posterior to refine my estimate over time. So it's a way of combining prior knowledge about the world with sensory input in an optimal way to make optimal inferences. Okay, so the question is, does the brain do this? Does the brain do Bayesian learning? And to do that, it would need to do two or three things. It would need to learn about the statistics of the outside world. It would have to learn the prior distribution of possible things that can happen. And it would need to also know something about how noisy our own sensory apparatus is to estimate the likelihood. And then, given these two, it would have to multiply them together and normalize them in a Bayesian way. So let me give you an example where that sort of thing might be useful. Imagine you're playing tennis, and the ball is flying over the net towards you, and you want to estimate where the ball is going to bounce. Well, Bayes' rule says there are two separate sources of information you could use to estimate that. You could use your sensory input to estimate the likelihood. Based on vision, audition, perhaps integrated over time, you might estimate the ball's most likely to bounce here, but because you know there's noise in your sensory apparatus, there may be some Gaussian cloud in this case of other possibilities. It's less likely to bounce here, it's definitely not going to bounce over here. But Bayes' rule says there's another source of information, not available in that current shot, but only available by repeatedly experiencing the game of tennis. That's that the ball doesn't bounce uniformly over the court when you play a tennis match. There may be some distribution with which the ball bounces, depending on your opponent's strategy and their skill level. And if they're a very good opponent, it may be that they distribute the ball in this green area here, the prior distribution of where the ball may bounce. Now, what Bayes' rule says is because there's uncertainty in the prior and there's uncertainty in your sensory input, the best thing to do is to combine them together. And to do that, you multiply the numbers here in the red by the yellow, renormalize, to get a new distribution shown here by these concentric ellipses, saying the most probable location is there. And the question we wanted to address is, when we learn these sorts of skills, do we do this? So what we do is we abstract away from this task. And I'm actually not going to tell you the real task we did. I'm going to give you a cartoon of the task because it'll capture really the idea. And the idea is very simple. A ball is going to appear somewhere in one dimension on the screen and then vanish after 50 milliseconds. So a ball is flashed up on the screen and then goes away. So there's the ball and then it vanishes. And the only task the subject has is to point as accurately as they can to where the ball was. And they do 2,000 trials of this. It's incredibly boring. We pay them lots of money to do it, but we can record what they do. But unknown to the subject, the ball doesn't appear equally likely over that one-dimensional line. In fact, what we're doing is drawing the ball's location from a Gaussian distribution, okay, with a standard deviation of 0.5 centimeter. So if repeatedly doing this task, the subjects could internalize the fact that there's some distribution. And the question is, do they do that, and do they use that distribution in a sensible way? So what we think happens is when they see the ball, because it's so brief, we know there's visual noise. And so if we show the ball, for example, at 0.5 centimeter, we expect that the likelihood will have some Gaussian distribution centered around the ball. You're most likely to see it at the actual location, but there's some chance you'll see it 0.1 millimeter to the left or 1 millimeter to the right. It's very unlikely you're going to see it a centimeter to the right. But because of visual noise, there'll be some distribution shown by this red. So how could you do this task? Well, one way would be just rely on your visual system. Wherever you see it, that's where you point. And therefore, if we look at all the trials out of the thousands we do where the ball really was at 0.5 centimeter, and we look at just those trials, what we'd expect you to see you do is you should point on average on the target, but there'll be some spread around the target due to visual noise. And that's one way to do the task. Now, it turns out that's a very suboptimal way to do the task, because we know what the optimal thing is. The optimal thing is to do Bayesian integration or Bayesian estimation. And what Bayesian estimation would say is, I know that there's noise in my visual system, but I've learned there's some distribution of the ball. Therefore, if I see it at 0.5 centimeter, I know it could have been at 0.4 with noise pushing me to the right, or it could have been at 0.6 with noise pushing me to the left. Both of those are equally likely. Noise is unbiased, and therefore it's just as likely that noise pushed me to the right as the left. But if I look at the underlying distribution of possible ball locations, the prior, it's higher at 0.4. So actually, it's more likely the ball was at 0.4 with noise pushing me to the right than was at 0.6 with noise pushing me to the left. And so the right thing to do if you sit at 0.5 is to point slightly to the left. And you can formalize that very simply by doing the Bayesian thing, which is multiplying these two curves together pointwise, and that's shown here. That's the posterior. And note the posterior, the peak, is moved towards the mean of the prior. Meaning that if we look at all the times when the ball really was at 0.5, people should point to 0.4. Meaning the optimal thing to do is to miss the ball on average. Now this seems surprising. I'm telling you the optimal thing here is to miss the ball on average. When the ball really is at 0.5, you're going to point to 0.4. How can that be a good strategy? Well, the reason it's a good strategy is doing the naive thing. On average, you're on target, but you have a big spread. But if you shift and do the Bayesian thing, what you buy is a much smaller spread. So although you're slightly biased now, in that you miss the ball on average, your spread is smaller, so your mean squared error is smaller. And this is interesting. What it says is if you watch someone do a task and they're missing on average, you can't infer they're not optimal. If you're an observer of someone doing this task, you might say, oh, they're missing on average, they could do better than that. But it turns out they can't do any better than that because you don't know the statistics which we've applied to this person. And I wouldn't tell you all this if it wasn't exactly the case. This is exactly how subjects behave. What we see is they're biased towards the mean of the prior. That's they shift their pointing. And as we do a generalization task where we blur the visual information, they become more and more biased. And in fact, we can extract this prior which best accounts for our subject's behavior, and that's shown here. Here's the true prior in red, and these lines for each subject and each condition, the prior that best accounts for subject's behavior. Suggesting they were doing a really pretty good job of internalizing this Gaussian distribution. When we questioned them afterwards, they had no ability to verbalize that there was anything interesting about the distribution. They thought the ball was just randomly appearing. But yet, their motor system was able to use this information. So it seems that the sensorimotor system has the ability to represent the statistics of tasks and has some knowledge of its essential uncertainty and combines those two in a Bayesian way. So it seems that Bayesian learning may be an important part of skill learning. So what I've really set up to now is that the brain has got some way of estimating the statistics of the outside world and learning that. And I made it sound as though getting this likelihood, the probability of sensory input given different states, was easy. But it's not easy for the brain. It's not clear how we should do that. When you send a motor command out and you get sensory feedback back, that transformation is governed by physics, the physics of our bodies and our receptor. But we and others long before us have suggested that within the brain you may have a neural simulator of those physics, a little predictor which taps off a copy of the outgoing motor command and basically tries to predict the sensory feedback you're going to get based on your outgoing motor command. So as I'm moving around in the world, not only am I sending a motor command down my arm, but I'm tapping off a copy of that and anticipating or predicting the sensory feedback I'm likely to get. And you can see how you would learn that. You could then compare this predicted feedback with the true feedback and use some supervised learning rule to update parameters of your predictor to make it a better predictor. Why would that be useful? Well, there are various uses. One is it's very useful for controlling systems with long time delays. If I have to wait for sensory feedback to come back, it can take 100, 200 milliseconds. That's very slow. If I can anticipate the feedback, I may be able to run on that anticipated feedback rather than waiting for actual feedback. Or perhaps I could do mental simulation rather than actually enacting movements. I could simulate them in my head and choose between different possible actions. Well, it turns out that we can actually do likelihood estimation by using these predictors, or predictors. And the idea is very simple. Rather than having one predictor, we're going to have thousands of them. Now, I'm just going to show you two here, just for simplicity, but you can generalize this to 1,000 if you want. And the idea is as the state of the world changes, so do the sensory consequences you're going to get based on your motor acts. So, for example, here's a predictor which has learned to predict for empty teapots. And here's a predictor which has learned to predict for full teapots. So for the same motor command, they're going to make different predictions. So if you send a motor command down, this one will predict it's going to move a long way, whereas this one will predict it won't be very far for the same motor command. So you can make parallel predictions based on different hypotheses of the state of the world. But then you can compare these predictions in parallel to the true sensory feedback. So we compare these predictions with true sensory feedback to get prediction errors. And the point is these prediction errors tell me about how likely it is I'm in these different states of the world. For example, if I have a small prediction error here, it's highly likely the teapot's empty. If I have a large prediction error here, then it's low likelihood that the teapot's full. And we can generalize this to arbitrary states of the world. So by making multiple parallel predictions, we can effectively get estimates of this likelihood. Now, I'd love to spend 10 minutes telling you all the evidence there is that the brain makes multiple parallel predictions about the world, but there's none at all. This is just a theoretical model at the moment, and it's actually very difficult to prove behaviorally that the brain makes multiple predictions. So instead, I want to persuade you at least the brain does make sensory predictions and compare those to actual sensory feedback. And to do that, I'll tell you about some work we've done on sensory filtering in humans, which really convinces us that the brain does make sensory predictions and compare those to reality. And again, the idea is pretty old. The idea is that our sensory apparatus receives conceptually two different sources of information. But when they get to the receptor, they're mixed up. So there's ex-afferent information. That's changes in the outside world that just happen. So things happen and I get to sense them. So as I hold this ketchup bottle here, someone taps on it very kindly for me, I get an external source of sensory information as a function of time due to that external event. But then there's another source of sensory information, that's reafferent information. That's changes I cause to happen and which I sense. So if I choose to shake the ketchup bottle at the same time, I'm going to get an internal source of sensory information due to me shaking it. But from the receptor's point of view, these are just combined together in a combination of ex-afferent and reafferent information. And there are reasons to believe that the brain would want to distinguish between these two. Perhaps it's more interested in things which are behaviorally relevant in the outside world, and therefore wants to be more attuned to those than to your own sensory information, which could be thought of as noise. And there are other reasons I'll come to later why you might want to distinguish whether I've caused something to happen or you've caused it to happen instead. And one way to deal with this problem is very simply, based on the command I send out, predict the sensory feedback I'll get based on my actions. So predict the reafferent information, subtract that off from the total sensory feedback, and hopefully the discrepancy tells me about ex-afferent information. So as I go around in the world, I predict what should be happening based on what I'm doing. Everything left over is you or the outside world. So what evidence is there that humans do this sort of prediction? Well, there's one very clear example, which is a very good candidate. And that's our inability to tickle ourselves. So back in the 70s, Weizkrantz did a seminal study where he showed if you self-administered a tactile stimulus, it felt as less ticklish than external stimulus applied to you. And he hypothesized that perhaps it was because the brain predicts the sensory consequences when you do things to yourself in a different way from when they're done to you by someone else. But back in the 70s, he didn't have the technology to actually prove this theory. So we can bring his experiment in the 21st century by applying robotic technology to ask the question, why can't you tickle yourself? And the system's very simple. Subjects hold a stick in one hand attached to a robot that can move in 3 dimensions, and they're going to move that back and forward. And we can track that in real time and use it to control another robot, which has got a small stick on it with a foam tip, and that's going to tickle the subject's palm. And the point is they move this one back and forward, we do various things here, and we ask them to rate a bunch of things, including how ticklish is it. So the first thing we can do is we can replicate Weizkrantz's study. Subjects move back and forward, and here I'm not showing you the robots, just the sticks. They move back and forward sinusoidally, and we replay as accurately as we can to the other stick that motion. So although the 2 sticks are physically separate, if we get the simulation right, it's like you're physically touching your hand with a stick. And compare the sensation in the same subjects to a situation where this hand is now still, but they get a sinusoidal input to the left hand. So the important point is the left hand gets the same input, a sinusoidal tickle in both cases. In this case, you cause it. In this one, you don't. And no surprises, what we find is the tickle rating is significantly less when you do it yourself compared to when it's done to you by the robot. So that's nice. Our apparatus works. But there are 2 possibilities here. One is it's just gain control. When I do something to myself, just turn down the volume, non-specifically, so I basically filter out sensory information. Or the alternative is the brain is making a precise spatial and temporal prediction of what's going to happen and subtracting that off. So to distinguish between these 2 possibilities, we can put some perturbations in. So one perturbation we can put in is a time delay. This hand goes back and forward sinusoidally. Now we replay it to the other hand with a 100 or a 200 or a 300 millisecond time delay. So importantly, this hand always does the same thing, sinusoidal movement. This hand always gets the same input, sinusoidal tickle. All we're playing with here is the temporal causality between the 2. And as we go from 0 to 100 milliseconds, it becomes more ticklish. As we go from 100 to 200, it becomes more ticklish again. And by a 200 millisecond delay, it's equivalent to the robot just tickling you. So whatever's responsible for cancelling the tickle sensation, it's extremely tightly coupled to temporal causality. Rather than put a time delay in, we can put a spatial misalignment in. So now there's no time delay, the hand goes back and forward sinusoidally, and we replay that to the palm, but with a 30, a 60, or a 90-degree rotation. So the hand goes in one direction, the tickle stick goes in another, although they're completely coupled. As we go from 0 to 30 degrees, it becomes more ticklish. As we go from 60 to 90, it becomes more ticklish again. And by 90 degrees, it's equivalent to the robot externally tickling you. So whatever's responsible for cancelling the tickle sensation, it's extremely tightly coupled to temporal and spatial causality. The only thing which makes sense from our point of view is the brain is making a precise spatial and temporal prediction and cancelling that off. Importantly, we interleaved all these conditions because we believe that you would learn novel rearrangements, and we wanted to avoid that. Now, I have to say, this tickling study is the worst study we've ever run in my lab, because tickling on the palm with a foam tip, it's an evanescent phenomenon. It comes and goes. You need large numbers of subjects. It's possible to rate things on scales of 1 to 5. We hate this. So I have to say, we were looking for a better way to look at this cancellation phenomenon. And so in the intervening years, I had 2 children. These aren't mine. I have 2 daughters. It's hard to get a picture of them fighting. But one thing you notice about children on the back seats of cars on long journeys is they get into these fights, which start off very gently, and then they escalate quite rapidly to the point where you scream at them. Now, my children do this, and when I pull my 2 daughters apart or shout at them, sometimes they'll say to me, both of them, that the other person hit them harder. Now, my children don't lie. So I thought, as a neuroscientist, it was my job to explain how they could be both telling inconsistent truths. And we hypothesized, based on the tickling study, that when one child hits the other, because they're generating the motor command, they get to predict the sensory consequences on their hand and subtract it off in the same way as for tickling. But the child who's passively hit gets to feel the full blow because they don't get to generate motor commands, there's no cancellation. Therefore, if the child who hit retaliates with the same force, the first child will think it's been exacerbated or escalated. So we decided to test this in the lab. Now, we don't work with children and we don't work with hitting, but the idea is the same. We play a game with two adults. They're going to play a tit-for-tat game. So we bring two adults in, but we brief them in separate rooms. So they don't know the rules the other one is playing by. That's important. And they're going to play a game. And the game is as follows. Each subject puts their finger under a little lever attached to a motor, and there's a force transducer we can measure the force. So this is one subject, this is the other. And the game starts with one of the motors generating a small force, 1/4 Newton, on their finger for 3 seconds, then stopping. And this subject's been told, remember the experience of that force and use your other hand to apply the same force down onto the lever above the other subject's finger for 3 seconds, then stop. And this subject's been told, remember the experience of that force and apply it back to the first subject for 3 seconds, then stop. So effectively, they take it in turns to apply the force they've just experienced back to the other subject in a tit-for-tat game. So here is the number of turns, and here is the force level, and here's 1/4 Newton, which is what we expect if they're good at this task for tit-for-tat. And what we see in all pairs of subjects is something like this. Oh, sorry, that's what the apparatus looks like, and this is what we see in all pairs of subjects. We see a rapid escalation of the force. Over the course of 5 goes, the force gets up to about 5 newtons, which is a bit painful on the fingertip, and we stop them. And if we ask subjects, what rule do you think the other person was playing by? They would say things like, well, clearly they were being told to double it each time. So we see a 40% increase in force per turn. Now, you could argue there's lots of cognitive things going on here. Maybe the subject is very bad at this task. So to really nail down whether this is a problem with prediction, we can run another group of subjects on their own. So again, their fingers under a force transducer, the motor generates a presented force here, they experience passively. They then have to match the experience by using their other finger to apply the force down onto the lever above their finger. So they experience it passively, they then have to match it actively. And our prediction is when they have to match it actively, because they're generating the motor command, they'll predict the consequence and subtract some of that off. And here's perfect performance, and what we see is a very clear and startling 70% overestimation of force required. So if they experience something like 2 newtons passively, they apply 3.5 newtons back to get the same experience. Now you could argue these subjects are just hopeless at this task, so we have a control condition in the same subjects. Again, they experience passive force, but now we give them a joystick. We ask them to adjust the joystick, and the joystick controls the torque motor to match their perception of the force. And we know from other studies, in this rather unusual joystick to force, people don't have a predictive model of this. And what we see in this case is subjects are almost perfect. So it suggests that we see a lot of sensory attenuation to self-produced forces. Now, why is this relevant to my psychological friends? Well, there's another use for this mechanism of prediction. And that is, at the moment I can hear a voice speaking in this room, and I can see some arms moving in front of me. How do I know it's me who's speaking in this room, and how do I know someone's not passively moving my arms? Well, a very simple way to decide is I predict the sensory feedback I will get based on what I send to my vocal tracts and to my arms. If it matches reasonably well with what I get, below some threshold, well, I'll say there's a low discrepancy, therefore it's me who's doing it. If Luke rushes up behind me and moves my arms passively, well, I won't have predicted it. I'll have a large discrepancy. I'll say that's not me. So it's a nice way of labeling whether the movements are generated by me or someone else. But Chris Frith, back in the 80s, said, what would happen if this predictive mechanism went wrong? So if we had a broken predictor, what would the consequences be? Well, I'd generate commands, and my arm would move and I get sensory feedback. But I wouldn't have predicted it. And therefore, I'll get a large discrepancy due to my own movements, and therefore I'll say it's not me. And in fact, this is just a symptom you see in some patients with schizophrenia and delusions of control. They make normal movements, but claim their movements are not being controlled by themselves, they're being controlled by external agents. So what's the prediction in this patient group if they have a broken predictor? Well, it's a nice prediction, this. Normally in patient studies, we predict they'll be worse than normal subjects. But here, if you have a broken predictor, what that means is you should be better at our task of matching forces than normal subjects, because you don't have the attenuation. So unusual prediction, this patient group should be better. So we've run a study looking at 20 controls and 20 patients who have diagnosis of schizophrenia. They're on a host of drugs, so this could all be a drug effect, but it's interesting nevertheless, I think. Here's the control group in blue and the patient group in red on the control task. So they can both do the force matching given the joystick. When we look at our control group, again, we see a large overestimation of the force they have to produce, a large amount of essential attenuation. On the other hand, when we look at our patient group, what we see is they're midway in between. In fact, they're significantly better than our control group at matching the force. Now, they're not perfect, but they're halfway between full attenuation and no attenuation. So if we think there's some threshold you have to cross before you say it's not me, this patient group, on average, will be close to that threshold. Now, sadly, it turns out that we've now run a lot of normal subjects, 124. And if you look at the level of attenuation in 124, there's quite a range. So this just shows you the mean excess force. So if you're to the right of the zero, you attenuate. We have some strange subjects who don't attenuate. But the majority attenuate, but the amount of attenuation is quite variable. And therefore, we expect that if you have to set some threshold for where you say it's me, aren't me, these patient group will each have their own threshold. And therefore, it's hard on an individual level to say what attenuation level will you now have delusions of control. But it seems the brain definitely predicts sensory consequences. We see a large amount of cancellation, and defects may be related to delusions of control. Okay, so what I've really set up to now is there's some way of estimating the statistics of the world. We have possible mechanisms to estimate likelihood, although that's not easy to do, but you could do it with multiple predictors. And I made it sound like a number comes out this end. You know, what's my belief in the world? But the beauty of full Bayesian reasoning is, in fact, not a number comes out that end, but a distribution. For every state you want to consider, it tells you the probability of that state. So if you're doing Bayesian inference, and there's some target out there in one dimension, so here's possible target positions, then the Bayesian inference will give you a distribution of possible locations. So here's the posterior probability of different target positions for a one-dimensional target. If I told you that a target was distributed like this, and I said to you, where do you want to point? You wouldn't really be able to answer that question unless I told you how I was going to penalize the errors you made. So in order to do full Bayesian decision, we have to decide how we're going to penalize errors. And once you tell me the penalizing errors, which we call a loss function, which tells me how bad is 2 centimeter error compared to a 1 centimeter error, then you can tell me where you should point. So for example, in statistics, when we fit a line to a bunch of data points, what we're implicitly saying is my loss function is quadratic. Meaning what I'm penalizing is the vertical deviations between the line and the points squared, summed up over the points. So effectively I'm saying what the loss function here is a squared loss function. A 2 centimeter error is 4 times as bad as a 1 centimeter error. Why do we choose a squared error here? Well, there may be some good reasons, but one reason is you can differentiate x squared. You can't differentiate absolute value of x, and therefore you can get an analytic solution of how to fit lines. But when it comes to neuroscience and humans pointing at a target, it's not clear what the loss function should be. Should it be quadratic? Should it be linear? And so we want to ask the question, in pointing, what loss function should people use? Or do people use? Well, to answer that, we developed a virtual pea shooter task. We give subjects a pea shooter, and we're going to ask them to point the pea shooter at a target, and the pea shooter is going to spit out peas. But unfortunately, this pea shooter does not come from Hamleys or FAO Schwartz, the most expensive toy shops in the world, because their pea shooters shoot up peas one after another in a straight line. This pea shooter comes from Toys R Us, and the peas scatter out all over the place out of this lousy pea shooter. But importantly, they scatter out with a distribution with experimental control. So effectively, we determine the distribution with which peas are going to be selected. And this shows one such distribution on a particular trial. So all subjects can do is choose how to point the pea shooter, which moves the distribution left and right. So as the subjects move left and right with a hand, it moves the entire pea shooter distribution left and right. And here's the target, and they're told, align the pea shooter to be on average as accurate as possible. Okay? And they don't get to see this distribution. What they see instead is peas being drawn at 10 a second from that distribution. So this shows the probability of different locations of the peas. So what they actually see is something like this. Peas coming up like this, and they adjust how they want to align that distribution to be on average as accurate as possible. On every trial, we change the distribution of peas. Okay, how does that help us infer the loss function? Well, here are just 4 different distributions we used, but we used many more than that. Imagine the loss function was as follows. If I hit the target, fantastic. If I miss it, it's equally bad however far I miss it by. So a miss is as good as a mile. So what would my loss function look like? Well, here's error in centimeters, positive errors, negative errors. If I hit it, 0, I get a very low loss. Fantastic. Anything else is equally bad. It doesn't matter how much I miss it by. So this is the maximizing the number of hits, or a miss as good as a mile loss function. So how should I align this distribution of p's with the target, if this is my loss, to minimize my loss? And hopefully it's intuitive. The best thing you should do is to line the peak of the distribution with the target. If you line the peak with the target, you're going to get the most p's on target. And therefore, the prediction of this loss function is subject to the line the mode, the peak of the distribution, with the target. On the other hand, if what I care about is the absolute error, so 2 centimeters is twice as bad as 1, then it turns out you can show very simply and analytically that whatever the distribution is, you should align the median of that distribution with the target. And for these skew distribution, that's a different location. On the other hand, if what you care about is squared error, so quadratic cost, then it turns out again, you can show very simply and analytically, for any distribution, the best way to minimize the loss is to align the mean of the distribution, which is a different location again. So by looking at how people align the distribution, we can infer what their loss function is. Okay, this just shows a sort of skewness parameter, and this shows, well, the details don't really matter, where they place the mean of the distribution relative to the target. Ignore all that, this is subject's data. We can look at the predictions of the models. Here is the miss as good as a mile model. Here is the absolute error model, and here's the mean squared error model. So none of those fit particularly well. So we can say, well, let's parameterize this. In fact, all those 3 models are really error to the power of some alpha. And so this is error squared, this is error to the power of 1, and it turns out this is error to the power of a very small number. So by looking at error to the power of some alpha, we can get a significantly better fit, but not a great one, by error to the power of 1.7. Now that's interesting. 1.7 is less than 2. And one thing you know when you do linear regression is linear regression is extremely sensitive to outliers. So there are things called robust estimators, which are better at ignoring outliers. And the point of robust estimators is they have exponents of less than 2. So it seems our subjects are doing robust estimation. They're more robust to outliers than a quadratic cost function would allow. And in fact, we can get a much better measure by doing non-parametric fits shown here, which shows a quadratic cost and the cost which best explains our subjects. And what it seems to be is that for small errors, people worry about quadratic errors. But as the error gets larger, they become linear. And in fact, this is a very famous statistical robust estimator called the Huber function, which does exactly this. So it suggests that when we do these sorts of tasks, mean square error actually is a pretty good approximation to what we do for small errors. But as the errors get bigger, we see that we're robust to outliers. Now, it's not true that all our subjects behave the same way. This is the group average. And in fact, I'd hate you to go away without knowing whether you are personally a robust estimator or not. So this is the audience participation part of the talk. The question for you is, you see blue dots over the entire screen. Where would you put a vertical red line to be as near as possible to all the blue dots? Okay? So you can translate the vertical line, but you can't obviously get through all the blue dots. And the question is where you would put it. And the point is that we can think about different losses. We can think that maybe your loss is the sum over all the dots of the error between the line and each dot to the power of alpha. And then you could say, where should I put the line if alpha was 2 or 1 or 3? And the point is that each of these lines corresponds to a different level of alpha. So I'm hoping you're all in that range, or I'm really worried. If you could all choose one of those lines as to where you put your vertical line to be as near as possible to all the blue dots, I'll reveal at no charge your personal alpha level. Okay, so have a look at your lines and follow your line down to your alpha value. So if you're to the right of this dotted line, it means you're not a robust estimator. It means you really worry about these outliers even more than linear regression does. If you're to the left of this line, then, like our subjects, you're a robust estimator. Can I have a show of hands? Who was to the right of the line? Right of the line. Okay, about 10, 15 people. Who's to the left of the line? Pretty much everyone else. Okay, great. But that's what we normally find. In fact, normally find about 85, 90% are robust estimators, and the other 5, 10% are non-robust. We haven't yet done the psychological profiling to work out what the real difference is to those who don't like to stand out in the crowd. That's probably for a different lab. But it suggests in general, when we're doing motor control, people are more robust to outliers than linear regression. Okay, we've done all this wonderful estimation. We know how to penalize errors at the end of the movement, but now we actually have to generate a movement. And the problem, I'm sure all of you will know, is that tasks are specified at symbolic levels. I want to dance, I want to hit a tennis shot. But movements have to act on 600 muscles in a particular sequence. And there's a huge gap between that symbolic level and the movement level. And for those who aren't familiar with this, take the simplest of all possible tasks, but it's true for any task you look at. Imagine I want to move my hand from this point in space to this point in space. Well, I could choose to move either with a fast or a slow duration, or any other duration. If I choose a particular duration, well, I can move my hand between the two with infinitely many different paths. Having chosen a particular path, I can hold my hand on that path with infinitely many different joint configurations. And similarly, having chosen a particular joint configuration, I can hold my hand at that joint configuration either very stiff or very relaxed through co-contraction. So I have a huge amount of choice to me. Well, it could just be that we all choose our own sweet way of moving, but thousands of rather tedious studies, I have to say, have shown that humans are extremely stereotypical, both between repetitions of individuals and across the populations. So if you look at almost any movement, eye movements or arm movements, here are saccadic movements. So here's time, here's speed, here are 5 up to 50 degree saccades. Deviations from these sort of trajectories are, neurologically signs of disease. Arm movements are roughly straight and hand paths, have bell-shaped velocity profiles. And when you learn a new task, someone says, this is the way to do it, that's the best somehow. Well, it's clear that these sorts of movements have probably been around for a long time through evolution. And that's because we seem to have dedicated neural circuitry to actually identify biological motion, which actually conforms to the way we move. So if you take a bunch of dots like this and set them into motion, even if the information is extremely poor, you're immediately aware of what's going on. You know whether this person's happy or sad. You can tell me the age of this person. You can tell me whether it's male or female. And you can take these sorts of very poor information. If this was cars going around a racing circuit, you'd have absolutely no idea. And you can put them in motion, and instantly you know what's happening in this picture. And if you apply that sort of motion to something else, it's pretty convincing as to what's going on. So it seems that biological motion has been around for a very long time. And even more interesting, I think, is that if you violate biological motion, for some reason it's quite funny in our society. And some of you will know this gentleman, those of you who are a bit older than the youngsters in the room. This is John Cleese for the Ministry of Silly Walks. But just by violating the normal biological motion, it somehow is amusing to us. So the question really is, why do we choose these particular ways of movement out of all possible ways? And I guess we believe in Darwin's theory of evolution. We believe that somehow our fitness gets better through evolutionary timescales. And perhaps, although we all move roughly similarly, maybe there's variation in the population. Maybe some of us move better than others. And those who move better than others have got more chance of getting married and having children and giving them to the next generation and so on. So maybe on evolutionary timescales, movements get better and better. And perhaps through learning mechanisms as well, movements get better and better. And I think the fight in our field, or my field, for the last 20 years has been, how do we rate how good a movement is? If you could assign a value, a cost, to every possible way of achieving a task, then we could just rank them from best to worst, choose the best, and we're done. And the fight's been, what's the cost? And there have been some interesting costs. So the ones which have been sort of successful at predicting or modeling the data are those based on smoothness. And you can measure smoothness different ways. You can measure it as the jerkiness of the hand, or the rate of change of torques at the joints. And minimum torque change, minimum jerk have been quite successful at capturing the data. But fundamentally, I think they're both wrong. And I think the problem is that as a modeler, they're really unsatisfying for the following reasons. What would I like the ideal cost to be for goal-directed movements? I'd like it to make sense in terms of what the brain or evolution should care about. It's not clear to me why the jerkiness of my hand should be important on evolutionary timescales. If I'm carrying a full pint of beer, it's vital. But other than that, it's not so clear why jerkiness should matter. Second, I think if the brain's going to optimize this through its lifetime, it has to be able to estimate the cost or measure it. It's not clear how you're going to measure the third derivative of position or torque change. You could measure the torque in each joint, integrate it over the movement. The brain could do it. It's a lot of work to go to. It's not clear why it would want to do that. Third problem is you'd like it to generalize to different systems. Eye, arm, hand. You don't want to have specialized costs for every system. And obviously you want to generalize to different tasks, pointing, grasping, drawing. And the problem with these two is they don't really generalize. And obviously you want to reproduce and predict behavior. So we thought a number of years ago, what really limits motor control on evolutionary or behavioral timescales? And it comes back to the fact we work with these neurons which are noisy. We've got this noise going on in our head, these stochastic units, and therefore perhaps it's noise which is a fundamental limit on motor performance. And in fact, it's a particular sort of noise. So unlike engineers which like to have this sort of white noise added onto the signal, it turns out in the motor system, it's been known for a long time, the noise scales with the level of the motor command. So we call the signal-dependent noise. The bigger the motor command, the bigger the noise, or the bigger the force, the bigger the noise. So for example, if you wanted to generate some motor command as a function of time, this is your desired motor command, you can think of it as force, what you're going to get is a corrupted version due to noise, and the noise will look like this. It'll have more noise at higher levels of command, less noise. And in fact, for our model, we assume a constant coefficient of variation. So the standard deviation of the noise scales with the mean level of the command. And what that means is if you choose a particular sequence of motor commands, for example, here, and you repeat them many times, you'll get a distribution of possible outcomes of the movement. So imagine, for example, you're going to catch this ball which is coming towards you. You've decided to catch it at this point in space. Well, you could move to it in infinitely many different ways. You could move along this path, or you can move along this path here. But we can now calculate, effectively, the motor commands required to move it along this path, and then we could corrupt that with noise, play it through the system, and ask what were the distribution of final positions of the hand given that particular action. And what we might find out is it might evolve like this to show you the distributions of some ellipse or some other complicated distribution at the end of the movement. Now, if you choose to move a different way, you have different commands with different noise, playing through a very nonlinear system, so very non-intuitive, but one thing's for absolutely sure, the distribution of states at the end of the movement will be different. And so if you move in this particular way, it may be that your distribution will look like this. And the point is that these different distributions may be preferable. One might be preferable compared to the other. If I said to you, which way would you rather move, you might say this way because the ellipse is smaller. And so the idea is, of the model, is if you can specify the desired distribution, or what matters about the distribution, whether it be the position, the velocity, the force, the time, so on. So you say, given a task, what matters about my distribution? Then we can turn this around and say, can I find the optimal motor commands to control that distribution? Now, this ellipse can't be pushed into zero. If you squash it in one way, it's going to pop out in other ways. But you can tune your statistics to the task. So for linear systems, we come up with an almost analytic solution to this. This just shows the motor command for eye movements for a third-order linear model. The details aren't important. But if you model the eye, for example, as saying I want to move my eye a certain number of degrees in a certain amount of time, and I want to do it so as to minimize the variability at the end of the movement, to make the movement as accurate as possible, then you can predict the saccadic trajectories. And shown here in black are the true trajectories, and red are the optimal way of moving my eyes given signal-dependent noise. In terms of arm movements, here are the paths and velocity profiles. Again, if I say I want to move my arm to be as accurate as possible, then I can again predict the paths of the arm movements and the eye movements, the velocity profiles. So why were models of smoothness so good? Why did minimum jerk and minimum torque change look so appealing? And the answer is quite interesting. If you want to make a non-smooth movement, want to make a jerky movement, well, you can think of non-smoothness as making an abrupt change in velocity. I'm making move my hand or abruptly change the velocity. Well, for inertial systems such as the arm, to abruptly change the velocity requires a large motor command, big force. So if I want to be jerky, I'm going to have to put a big force in. Well, one thing we know about big forces, they put lots of noise in. So if I'm going to be jerky, I'm going to be inaccurate. So effectively, the reason you're smooth is because non-smoothness leads to inaccuracy because it has large motor commands. So you don't actually have to measure smoothness. All you have to have is signal-dependent noise and try to be accurate, and by default you will be smooth. But you don't have to measure smoothness. Okay, so you're not measuring smoothness, you're measuring accuracy, and the consequence of that is smoothness, which I think explains why minimum jerk and minimum torque change actually were able to capture a lot of data, even though I think they're fundamentally the wrong measure. So we've gone on to look at a lot of things. We've looked at the source of signal-dependent noise. We can predict the durations of eye and arm movements. We can predict other tasks, obstacle avoidance. You can put almost any task, however complicated, within the statistical framework. So we think we have a biologically plausible underpinning for eye, arm, and wrist movements that noise these statistics of movements, and you can control the statistics by choosing different ways to move. And I'm going to skip my very last part and say I hope I persuaded you at least that the brain devotes a great deal of effort to minimize uncertainty through Bayesian estimation, through predicting consequences of action, and by controlling specific action through planning. And sadly, I didn't really have time to tell you about our recent work on structural learning, but you can always download that from my website. I want to thank all my collaborators on this work, and just to remind you that when you see creatures doing what appear to be very simple tasks, the actual complexity of going on inside the brain is really quite dramatic. Thank you very much.